Consider a case in which you just put sugar into water, a sugar cube. Now, that sugar cube, some of the solid particles on the surface will have enough kinetic energy to break free from the solid and to get dispersed into the water to dissolve. So you might have in the first moment 3 sugar particles dissolving, and having no sugar initially dissolved, none of it will recrystallize onto the solid. So you give it another moment, and you should expect to have then 3 sugar particles dissolve. Now, you'll still have the same temperature and surface area about of your solid in contact with the liquid as before, and so you'll still have 3 dissolvings. But now that some sugar particles are dissolved, they can sometimes still collide with and rejoin the solid to recrystallize. So in this moment, we might have now a little bit of recrystallization, just 1 particle recrystallizing. If you give it another moment, having 3 dissolving and only 1 crystallizing, you should expect to have more dissolved in the next moment. So instead of having 3, we might have 5. Now you see that having a higher number of sugar particles dissolved, we should have then more able to collide with and rejoin the solid in the next moment. And so the rate of crystallization is higher, having a higher concentration of dissolved sugar. Give it another few moments, and soon you'll have 9 particles dissolved. Now, you still have 3 sugar particles dissolving in a given moment, but now having 3 times as much dissolved as when we had 3 dissolved, you now have 3 times as much recrystallizing as before. And so now you should have 3 crystallizations. What would happen in the next moment if you just let it sit here and didn't change anything? Well, you would still have 9 dissolved. If there were no change, still 9 would be dissolved. You've reached a point of equilibrium where you have equal rates in both directions. There are an equal number of dissolvings as crystallizations in a given moment. Having equal rates, we will not be changing the concentration of the amounts dissolved. And this is a standard condition at equilibrium. The concentrations or pressures of compounds will no longer change if you don't change the conditions. As we see, 9 remain dissolved. This, if you were to leave it like this, would give us a saturated solution, one which is essentially full. It contains the maximum amount of solute for a given amount of solvent at a given temperature. It's full. You think saturated solution, think full. Now, what if we were to add more solid? Could we dissolve more sugar within? All right, so consider a case where we were to add more solute. Now, having another chunk of sugar in there, you'll see that, presuming that it has about the same surface area as before, it will also dissolve at a rate of 3 particles per moment. But you see that in the previous case, with this certain concentration of sugar dissolved near our original sugar particle, 3 sugar particles crystallized. Here again, having about the same surface area as that original particle, 3 sugar particles will crystallize upon this. Having this new chunk here, we can have more dissolving, but we also have more crystallization in a given moment. In fact, these should be equal to each other. We've not actually been able to change the overall rate of crystallization versus dissolving here. So here in this moment we have 9 particles dissolved, and in the next moment there will be 9 particles dissolved. Even though we add more solute to the bottom, we cannot dissolve any more solute into the solution. We've reached the maximum amount of solute that we can dissolve in this solution. This solution is full with regard to this specific compound. Now, this is kind of more of a question for my AP and college students, but what if we were to add an entirely different compound, say potassium iodide here? Could that dissolve? Or is the solution full? Well, no, it's only full with reference to that sugar. If you were to put some other compound in, it's not full with reference to that, because there is yet no potassium iodide dissolved, and so there will be none crystallizing upon some chunk that you were to add. And so you could dissolve more potassium iodide. And so when we're talking about saturated solution, we're only talking about being saturated with regard to one specific compound. There's still plenty of room for other compounds to dissolve, which we'll see in solubility equilibria. So we said that we were saturated for this given amount of solvent and at this given temperature. What if we were to add more solvent? Consider where we double the amount of water from this case. Now, having doubled the amount of water, we still have the same amount of particles dissolved, but their concentration is only half of what we had previously. So though we have about the same temperature and surface area, and therefore 3 dissolvings in a given moment, we now have half the concentration of dissolved sugar versus before. And having only half the concentration, we'll have only half as many dissolved sugar particles colliding with and rejoining the solid as before. And so instead of having 3 recrystallizations, in this point we might only have, say, 1.5. Now we have a greater rate of dissolving than crystallization, and so we should expect for the amount dissolved to increase. In fact, how much would increase? Well, we were able to dissolve 9 dissolved particles in this original solution. Now, having twice as much water, we should have twice as many particles dissolved. Ultimately, we get the same concentration as before, the same number of solute particles per given amount of solvent, but having more solvent, we could dissolve more solute. And so here now we have, yes, 3 times the particles dissolving as before, but we also have now twice the concentration as before, twice as many as the 1.5 crystallizings. We have 3 crystallizings. And so we've reached another point of equilibrium. We've reached our saturated solution again. Now, what if we were to increase the temperature here? Well, taking our original saturated solution and increasing the temperature, we might perhaps, if you were to increase the temperature by, say, 20 degrees Celsius, we might multiply the number of dissolvings by 3 times. Instead of having 3 dissolvings in a given moment, we might have 9. Now, we have greater rate of dissolving than crystallization, and so we should expect for the amount dissolved to increase. Yes, it should multiply by 3 times, so that now, instead of having 3 crystallizations, we have 9, the same amount as those dissolving. And so we reach a point of saturated solution again. We can see that increasing the temperature will increase the amount of solute dissolved. So generally, for solids, you increase the temperature, you increase the amount of solute that can dissolve. This is the case for solids, but it's actually opposite case for gases, which we'll talk about later. Finally, what if we were to add just a small amount of solute, so that actually all of it was able to dissolve into the solution? Perhaps the solution can only dissolve 9 particles in that given amount of liquid, but we only added enough solute to have 7 particles dissolved. Well, I guess the solution is not full then, is it? You could dissolve up to 9. It's not full. It's not saturated. It's unsaturated. It's an unsaturated solution. It doesn't contain the maximum amount of solute for a given quantity of solvent. So a good clue that you have an unsaturated solution is there's no solid at the bottom. A good clue that you do have a saturated or full solution is even though you've stirred it long enough to reach an equilibrium, some solid still remains at the bottom. You could not dissolve more. You were not able to dissolve more because the solution couldn't dissolve more. It was full. Having solid at the bottom is a clue that you have a saturated solution. Thanks for watching, guys.